Okay, well, we're back here for the second part of our lecture, second video on this lecture on properties of slope. In the first part we talked about defining slope and numerical computation of slope and graphical interpretation of slope. We talked about its connection to steepness, about parallel and perpendicular lines, and vertical and horizontal lines as they relate to slope. In this part we're going to talk about contextual interpretation of slope as an average rate of change, and talk about what happens if we have some nonlinear functions. Can we still talk about slope on those? And what does that tell us about the graph, about whether it's increasing, decreasing, or constant, concave up, concave down, or linear? And then of course we'll have a part 3 that we'll get to a little bit later. So let's start with this example here. We have a table where we have time in hours, t, and the position, p, in miles, say mile markers on an interstate or something, and compute and interpret the slope between 2 points. So we want to find all the slopes between each pair of successive points. In other words, the slope for each time interval. So the time interval from 1 to 3, the interval from 3 to 4, and one from 4 to 7. So we're going to compute 3 different slopes here. Well, they may be different, they may be the same, we don't know yet. But compute those 3 slopes and tell me if this is a linear function, and if it is a linear function, what's its formula? Okay, go ahead and do that now. Press pause. Okay, well, you're back. Hopefully you've already computed these slopes. And of course, to do that, we need to find delta y and delta x. Delta y, well, y is p in this case, so I'll call it delta p, the change in the output. And the change in the input, normally we call it delta x. Well, here our input's t, so we'll call it delta t. So delta t is the change in t, or differences in t. So from 1 to 3, the delta t would be 3 minus 1, or 2. In other words, we're adding 2 to the t there. Similarly, for the next interval, going from 3 to 4, delta t is 1, and from 4 to 7, delta t is 3. We similarly compute delta p, the differences in the p's. So 5 minus 2 is 3, 8 minus 5 is also 3, and then 16 minus 8 is 8. Now, we're not really so much interested in delta p and delta t individually at this point, but rather in the slope, which is the ratio of the two, or divide delta p by delta t. So we get miles per hour. So for the first interval there, we're dividing 3 by 2 to get 3 halves, or 1.5. For the next one, we divide 3 by 1 to get 3. And the last one, we divide 8 by 3 to get 2.6 repeating, or 8/3. Well, we see that we need now to interpret these slopes in context of the problem, and is this linear or not? So, did these agree with the numbers you came up with? How do you interpret these slopes now? Well, these slopes is the average rate of change between the 2 points. So in this case, it's a distance traveled over an interval divided by the duration, or length of time, for the interval. So this is a rate of speed, or maybe velocity, measured in miles per hour. So in other words, our average speed from time t equals 1 to time t equals 3, over that 2-hour period, we averaged 1.5 miles per hour. Okay? From time 3 to time 4, we averaged 3 miles per hour. And for the last one, from 4 to 7, we averaged 2.66 miles per hour. Hopefully that's not in a car. Hopefully that may be maybe walking, running, or something like that. Is this a linear function? If so, what's its formula? Well, for a linear function, we have to have a constant average rate of change. In other words, a constant slope. These slopes are not all the same. We do not have a constant slope, so this is not linear. Now, we don't know what a formula for this is, at least not yet, and but we do know one thing: it's not linear. So it's not y equals mx plus y0, for example. It's not a linear formula. It's some other kind of formula. So if we arrange the points in a table so that the input values increase, and we find the slopes between pairs of successive points in the table, what's that going to tell us about the shape of the graph of a relation? That's going to be our main question that we're going to be looking at for the next few slides. So let's take a look at some examples here. I've got 3 different functions, function f, function g, and function h. And I want you to compute the slopes between successive points here want you to do this for each pair of successive points. And I want you to tell me, what do these slopes tell us about these particular graphs? What do you know about the graph shape just by looking at the slopes? And then what I want you to do is assume that these are defined, well, at least they're defined on that interval. Like, for example, f is going to be defined on the interval from 10 to 13. It's defined for things between 10 and 13, but not necessarily outside of that. The same thing for g. It's defined between x is going from -4 to -1, but not necessarily outside that. And h is defined from 0 to 3, but not necessarily outside that. And so you want to take those and graph these ordered pairs on the graph, and then connect the dots between the one on the left to the one on the right, and connect them going through all the dots, and with the sort of a smooth curve. And then tell me what you know about the shape of these graphs. If it's appropriate, use a straight edge. If it's not, then don't. Okay? Do this on graph paper, and what I want you to do, though, before you graph it, is tell me, just by looking at the slopes, what should you see in the graph. Then graph it and see if that checks out. Be sure you do this yourself. Now, press pause. Okay? Well, if you notice the first one, function f, we have slopes of 0 every time. Well, we know that if we have 0 slopes, it's a constant function, and the fact that all the slopes are the same makes it linear. So we should see a little piece of a horizontal line, and if you graph those points and connect them up, you get this little red line segment that you see over here labeled f of x, and you can see that here. The dark blue one, g, we see the first time it goes, well, delta x is 1 every time, so in this case delta y will be the m. So it's going down 1.5, down 1.5, down 1.5. So delta y is -1.5, and since delta x is 1, the slopes are also -1.5 every time. The fact that we have negative slopes says when we go to the right, we go down. So that makes it a decreasing function. The fact that all the slopes are the same makes it a constant slope. That makes it a linear function. So when we graph this, we should see a little piece of a straight line, a line segment. And in fact, when we graph those points, you can see it here. And for example, here is the point at the end of this g is the point -4, 7. We go the right one way down 1.5, right one down 1.5, right one down 1.5. That makes it straight. So constant slopes are linear functions. The light blue one here, the last one has positive slopes. They're always 2. Again, I'm picking delta x to go up by 1, so delta y is the slope, and notice we're just going up by 2 every time. So we have positive slopes. Just the fact that they're all positive says we're always going to the right, we're going up. So that makes it increasing, but the fact that they're the same means we're increasing at a constant rate. Increasing at a constant rate. That is a constant average rate of change. That is a constant slope. That is a linear function. So this should be a straight line, and every time we go the right one, we go up 2, which you can see here on the graph. Now the next question is, what if I give you something like this, but what if they're not always the same? What can that tell us about the graph? So before we go on, if we arrange the tables, points in a table so the input values increase, what do slopes between pairs of successive points tell us about the shape of the graph or relation? What if all the slopes are positive? What does that tell us? What if all the slopes are negative? What about if all the slopes are 0? And then what if the signs of the slope are some positive, some negative? They're not all the same. What does that tell us? Well, the slope is the amount of vertical change divided by the amount of horizontal change. By arranging our table in increasing values for the input, we're always having a positive delta x from one to the next. So we're moving to the right on the graph. And the sign of the slope is then the same as the sign of delta y. So if the delta y's are always positive, we're going up, and the delta y's are negative, we're going down, but we're always going to the right. So that means that the slopes are all positive, the graph is increasing. If the graph is increasing, the slopes are positive. If the slopes are positive, the graph is increasing. The slopes are negative if and only if the graph is decreasing, and the slopes are constant, the graph is constant if and only if the slopes are all 0. If the signs of the slope change, okay, some positive, some negative, that means sometimes it's going up, sometimes it's going down. So it's not consistently increasing or decreasing. What if the slopes are constant, and what if the slopes are changing? What do we know about that? Well, that's right. We know that if the slopes are constant, it will be, it's if and only if it's a linear function. If the slopes are changing, then the function is not linear. It will have some curve to it, some curvature or concavity. What if the slopes are consistently increasing, and what if the slopes are consistently decreasing? We're going to examine that in our next exercise. So here are four functions, P, Q, R, and S. And again, I've chosen delta x to be 1 each time. Let's find the slopes between successive points, and I've arranged these so that the x's are going up by 1 each time, so they're going from left to right on the graph. Okay, what does that? Find the slopes, and then just by looking at the slopes, is there anything you can tell us about it? Can you tell if it's increasing or decreasing or constant? Can you tell me if it's linear or not? Can you tell me something about the shape, which way it's curving? Okay, go ahead and do this now. And again, like the last time, we're going to assume P of x, for example, is defined between 0 and 3. Graph those 4 points and just connect them. Don't necessarily extend outside of from 0 to 3, but inside it should be connected with a nice smooth curve. And similarly for the others. So we're going to get 4 little short pieces of graphs, and tell me what you can see about these. See if you can tell just by looking at the slopes what your graph is going to look like, and then look back at your graph and look back at your slopes and see if you can compare those and get some find out how the structure of one affects the structure of the other. Okay, please go ahead and do this now. Get some graph paper out and work this out. Press pause now. Well, we see that the first one, P, which is the pink one, we're going up by 1, then up by 3, then up by 5. Now that's always a positive slope. So the fact that we have positive slopes says when we go to the right, we're going up. So that's an increasing function. However, it's not increasing by the same amount each time. Let's look at the pink one here. The first one, we go to the right 1 and up 1. Then we go to the right 1, we're up 2. We're going up faster the next interval. And the last one faster still, right 1 and up 5. So this is curved to it. It's not straight. Those slopes would all have to be the same to make it straight, but it's curved. And if you remember from what we talked about earlier, this is concave up. It's part of a right side up bowl. So this is increasing concave up. Now the brown one here, Q, that's over here, notice it also has positive slopes, but the slopes are decreasing. 5, 3, 1. The first one, the slopes were increasing, 1, 3, 5. Okay? And so this one is 5, 3, 1. So we have decreasing slopes this time. And look at it, we're going the right one up 5, right one up 3, and then right one up 1. And so it's curved the other way, so that this is concave down. Still increasing, still positive slopes, so it's still going up. It's still an increasing function, so going up as we go left to right. But the rate of increase is decreasing, so it's concave down. The pink one, P, was increasing concave up. The rate of increase was increasing. So it was increasing concave up. Now the red one, notice it's going down. R is the red one. And so it's going down 5, then down 3, then down 1, going to the right one each time. And so here's the red one. Go right 1, down 5, right 1, down 3, right 1, down 1. This is all the slopes are negative, so every time we go to the right, we're going down. Negative slopes say it's a decreasing function. But the slopes are actually increasing. Now remember how we order negatives. Negative 5 to negative 3 to negative 1 is increasing. It's left to right on a number line. Okay? And it's still, which shape is it? Well, it's still part of a right side up bowl. It's the decreasing side of a right side up bowl. So that's decreasing concave up. So if you notice, in both cases where we had increasing slopes, we had concave up. And of course we got the other case in the last one. The last one is consistently negative slopes, negative 1, negative 3, negative 5. That's going to make it decreasing, but let's look at it. Right 1, down 1, right 1, down 3, right 1, down 5. Okay, and so we see, we see that it is decreasing at an increasing rate, so it's falling faster and faster and faster, more and more each time, And so these slopes, though, are actually decreasing numbers. -1 to -3 to -5 is decreasing, going left to right on a number line. Right to left, decreasing. And so decreasing, that should say decreasing slopes, so it's concave down. These are both labeled wrong. I'll fix that. So the two that with increasing slopes were concave up. That was the pink one, P and R. And the two with decreasing slopes were the brown one and the blue one. That's Q and S. Those should say decreasing slopes here and here. I'll fix that for the handout. Those are concave down. That part's labeled correctly. So we've seen that a function will have constant slopes if and only if it's a linear function. If the slopes are changing, it will not be linear. It'll have some curvature or concavity to it. A function's concave up on the interval if and only if the slopes are consistently increasing on that interval. That's like curved like a right side up bowl. If they're consistently decreasing slopes on the interval, then the function is concave down. Okay, so it's concave down on the interval if and only if the slopes are consistently decreasing. So that's like an upside down bowl or like an umbrella. So increasing slopes will be concave up, part of a right side up bowl, like a smile, like this. So there could be decreasing or increasing, but it's concave up because the slopes are decreasing. So like over here it might be -5, then -4, -3, and here's -2, -1 somewhere, close to 0 down here, 1, and here's 2, up here's 3. So the slopes are increasing as we go across this way. If we pick successive points on this one, upside down bowl, that are a frown, that's concave down, and that's decreasing slopes. So down, frown, smile, you're up there. So let's summarize. The sign of the slope tells us the direction of the graph. Positive slopes if and only if it's an increasing function. All negative slopes if and only if it's a, that should say decreasing function. That's what I get for copying and pasting and not fixing and everything. Okay, 0 slopes if and only if it's a constant function. Increasing slopes, so changes in the slopes tell us about the concavity of the graph. If the slopes are always increasing, then the function's concave up. If the slopes are always decreasing, it's concave down. And if the slopes are constant, it's a linear function. So if it's always sort of behaving the same way, we have 7 possibilities for basic graph shapes. So if the slope is always 0, then that is a constant slope, so it's linear and it is a horizontal line or constant function. If the slopes are positive, we're increasing from left to right, either straight, concave up, or concave down. If the slopes are negative, the last column, they're always decreasing from left to right, straight, concave up, or concave down. If the slopes are increasing, it's concave up, like part of a right side up bowl, either increasing or decreasing. If the slopes are decreasing, we've got concave down, again, an upside down bowl or a frown, either increasing or decreasing. Now when I say these things here, I'm not talking about these specific graphs. I'm talking about the basic shape of the graph. Okay? So the basic shape is what I'm referring to here. So we have those 7 basic shapes. Now, not every function, however, looks like one of those 7 basic shapes, but most, we'll call them well-behaved functions, have one of the 7 basic shapes at least on intervals. But it may change from one of those 7 basic shapes to another basic shape, and points dividing these intervals where it changes from one of those 7 basic shapes to one of the others are called critical points. And there are 2 basic types of critical points, extrema and inflection points. Let's take a look at those. Some of this we've talked about a little bit before, back in our first unit. A neighborhood is the interior of a small circle centered on a point on the graph of a relation. Not the circle itself, just the inside of the circle. A point is a local maximum, or sometimes called a relative maximum, if and only if there exists a neighborhood, perhaps a small neighborhood, but some circle that you can draw around it, so that the point has the greatest y-coordinate in that neighborhood of any of the ones that are on the graph that are in that neighborhood. The graph changes from increasing to decreasing at a local maximum. A point is a local minimum or relative minimum if and only if there exists some neighborhood about the point, so some little circle around the point, so that the y-coordinate of that point is the smallest or least y-coordinate of any of the y-coordinates on the graph that's in that neighborhood. Okay? The graph changes from decreasing to increasing at a local minimum. If the point is the biggest, highest point, period, on the graph, that's called a global maximum or absolute maximum, if and only if the point has the greatest y-coordinate of any points of the relation. And it's a global minimum or absolute minimum if and only if the point has the least, that should say, least y-coordinate of any points in the relation. I have too many typos here. An extremum is either a maximum or a minimum. So a local extremum could be a local maximum or a local minimum. Global extremum could be either global maximum or global minimum. And if you want to make these plural, maxima, minima, and extrema are plurals of maximum, minimum, and minimum. So maximum, minimum, and extremum are singulars. Maxima, minima, extrema are plurals. An inflection point, or point of inflection, is a point where the concavity changes, either from up to down or down to up. It's still an inflection point. So if we look at this particular graph here, we have an endpoint on the right. Assume we have an arrow on the left, so that it goes forever down and to the left, but we have an endpoint on the right. Because the arrow down on the left, it has no global minimum. There is no lowest point. But we do have an overall highest point. That's the endpoint on the right. So that's a global maximum as well as being a local maximum. We also have a local maximum here near x is 0, just to the left of 0, and that's the highest point on the graph, at least in this close by. We could draw a little circle around that, and it's the highest point in that circle that's on the graph. The local minimum is down here, close to, just a little bit to the right of 4, and that's where we have a lowest point on the graph, at least close by. It's not overall lowest. There are lower points over here to the way over here to the left, but locally it's the lowest point. So it's like a valley, and a local maximum is like a peak, right? And then it changes concavity at this inflection point, which is right about here at about 2, and so we see it's concave down from negative infinity to 2, and concave up from 2 to infinity, or 2 to 7. It doesn't go to infinity, it just stops at 7 for x. So notice within these 4 parts, these key points kind of break it up into 4 regions, and within the regions it does look like one of those 7 basic shapes. So this blue part of the graph here, from negative infinity up to, well, almost 0, is increasing concave down. And from that maximum to the inflection point, the pink part of the graph, it's decreasing concave down. Then the green part of the graph, from the inflection point to the local minimum, is decreasing, but it's concave up. And the red part, from the minimum here to the end point, is increasing concave up. So we can break it down into pieces, and it looks like one of those 7 basic graph shapes. So we know, for example, over here, on all the increasing parts, the blue part and the red part, we have positive slopes between 2 points in those parts. And the pink part and the green part, we know, well, actually all the way from the maximum to the minimum, it's decreasing. So slopes between any 2 of those points in there, if we do successive ones, the slopes are all negative. If we look at the concave down part, the blue and the pink part, if we pick any 2 points in there, and then we pick 2 other points, and they're kind of going left or right, those slopes are going to be decreasing. Whereas the concave up part, the green and the red, if we take successive pairs of points throughout here, the slopes are going to be increasing. Okay, so there's a overview of some things about interpreting slope as an average rate of change, and also what the slope has to tell us about the graph in terms of increasing, decreasing, constant, concave up, concave down, and linear. Come back for part 3 of the lecture. We're going to talk about something called a difference quotient, symmetric difference quotient, and a little bit more about contextual interpretation of slope in some applications.